All right, thank you everyone for coming to my talk. My name is Jeremy Wagner and I'm a technical writer at Google for Chrome, focusing specifically on web performance and core web vitals. I am from Minneapolis, Minnesota, which if you don't know where that is, don't worry about it. It's a place. I guess you could say if you ever see a Minnesotan depicted on a television show, they kind of, sound like this, don't you know? And so that's really all you need to know. We're kind of a weird remote place, and the further north you go, the weirder it gets. So anywho, I'm honored to be in Seoul. My first time in not just in Korea, but in Asia, which is awesome, to be giving this talk about a new responsiveness metric that we've been working on at Google, called Interaction to Next Paint, or INP for short. So let's get rolling. So before we can get into INP, we need to clarify responsiveness. And when we talk about responsiveness, we're really talking about how quickly a user interface responds to a user's input. You've almost certainly experienced poor responsiveness. It occurs when you interact with something on the page, but the visual feedback of that interaction is significantly delayed. Poor responsiveness makes a page seem unreliable. And this unreliability means that you may have to tap multiple times on a page element, which can cause multiple unintended inputs, as you can tell in this video, or worse, no response at all. So we want good responsiveness because it gives a sense that a page is reliable in responding to what we want it to do. So what causes poor responsiveness? And to answer that, we need to talk about tasks. In order for a web page to provide a user experience, a web browser must orchestrate a lot of work. To do that, it uses threads. There are many threads, but the most important of these is the main thread. It's where most work occurs, including the work your JavaScript code queues up. Hang on. Oop. Each discrete piece of activity on the main thread is a task. And a task is made up of activity. In this case, we see that this activity consists of script evaluation and compilation. Now, each task takes the amount of time it requires to complete. However, if a task takes too much time, it affects how quickly the main thread can respond to subsequent tasks. And when that happens, that task becomes a long task. A long task is any task that exceeds 50 milliseconds. And the portion of the task longer than 50 milliseconds is known as the task's blocking time, which is the amount of time that the main thread is unable to respond quickly enough to new tasks. This is a significant source of poor input responsiveness. Long tasks can cause pages to be sluggish and unable to respond quickly to user inputs. But it's vital to remember that tasks drive everything that happens on the main thread, and that includes interactions. Here you can see that there's a single task that shows a loading spinner as a result of a key down event. These types of interactions, and far, far more, make up the user experiences that we use every day. And those interactions need to be fast, because what we want is visual feedback sooner. And that visual feedback comes in the form of a new frame that the browser paints. Hence the name of the metric, Interaction to Next Paint. One way of optimizing work in the browser is to avoid long tasks. Too many long tasks are a user experience problem. But more than that, it can also be the accumulation of many small tasks that can be problematic as well. In either case, the important thing to remember is that there is also time that the renderer requires in order to present the next frame. This involves some tasks that run on the main thread, such as style and layout calculations, maybe even stuff for request animation frame. But there's also time involved on the GPU and compositor threads to get the next frame ready to paint. It's just that long tasks are easier to identify in profilers, so they're really a great place to start optimizing. Now you might be thinking, come on, Jeremy, why are we talking so much about tasks? Tasks. That's all you're ever talking about. Well, the reason for this is the event loop, which is something I won't go into deep detail about, But it is important to know just a bit about it and how long tasks or many small tasks can sabotage the user experience. The event loop is a continuously looping task queuing mechanism run by the main thread. It loops around and around and around and around. It does this until a task is queued up. And when that happens, the event loop will pick up the task, a key up event handler in this example. And when the event loop has picked up the task, it processes it, and it pops it off the queue when finished. Then, if the task causes any changes to the layout, the browser has to do rendering work to reflect those changes before the next paint. When that rendering work is completed, the browser presents a new frame, which is the visual feedback from the task. If tasks don't become long tasks, or if there are a lot of small tasks that pile up in the queue, or aren't a lot of small tasks that pile up in the queue, everything goes smoothly. But when there is too much work, visual feedback is delayed, that stuttering, janky feeling you get when you scroll and things just aren't working, or like just animations aren't going as fast as they could be, and even outright freezing of the browser tab in some extreme cases, that's a problem. INP is a metric that quantifies a page's ability to avoid doing these things. This will be a quick rundown of how INP works, but for the full story, you're going to want to read the official documentation at web.dev/INP to get a sense of all the little nooks and crannies in terms of how it works. But because it is a complex metric, and I only have so much time, but I will do my best to summarize. INP is a metric that observes certain interactions using the event timing API. This API receives an entry every time the user interacts with the page and contains timings for those interactions. Unlike first input delay, INP measures more than just the input delay of the first interaction. If you don't know what an input delay is, don't worry, we'll get there. And finally, it chooses the single worst interaction, or close to it, which is intended to represent a page's overall interaction latency. It's a bit more complicated than this, so a little bit more on this in a bit. The takeaway from all of this is that INP is all about the time it takes for a new frame to be presented for the current interaction. From the time the operating system recognizes an input, for the browser to pick up that input, for the event handlers that drive it to run, and finally for the time it takes the browser to do all of the rendering work to show you the results of that work in the next frame. However, INP doesn't measure all interaction types, but it does measure most that drive user interactions. Those include keyboard interactions, mouse clicks, and taps on touchscreens. It's also important to call out what doesn't get taken into account for INP, at least directly. This isn't an exhaustive list, but just a few things that are important to call out. Hovering over elements with a fine pointer device, such as a mouse, don't count towards INP. However, because this is tricky, you could trigger animation work that may affect a soon-to-be future interaction. Think if you hover over a button that has a hover animation. If that work is occurring as the user clicks on the button, that may delay the presentation of the next frame. Network activity isn't factored into the duration of an event for INP. However, fetch requests are asynchronous and can have an indirect effect, especially if they land during a future interaction. Scrolling isn't taken into account either. However, that's a word again, however, users can scroll with the spacebar. So if an event captures spacebar inputs, that could theoretically queue up tasks that may affect that interaction, but the scrolling itself is not considered. All qualifying interactions are recorded throughout the entire life cycle of the page. When the page is unloaded for a new one, the page's INP is calculated by choosing one of those interactions. For pages with relatively few interactions, such as pages with mostly text and images, or just simpler applications with fewer input requirements, This is often the interaction with the most latency, or the slowest or worst interaction. However, some pages may have many interactions before they're unloaded, such as single-page applications and rich apps like in-browser games and other application types. In such cases, we don't want to penalize developers by selecting what could be an extreme outlier of interaction latency. In cases like these, the 98th percentile of interaction latency is selected. The resulting value is the page's INP. The idea is that by selecting the worst interaction on the page, or closest to it, you have a value that represents a page's overall interaction latency. Think of it this way. If your INP is in the good range, that is 200 milliseconds or less, all interactions on your page are reliably fast. If your INP needs improvement or is poor, then it's likely that most of your pages, or at least a decent chunk of them, all those interactions are too slow. But what does an interaction look like? The first part of the interaction starts with the user input from one of the interaction types we just discussed. For example, say a user clicks on a button to open a menu. When the user clicks, there is a period of time between when the user clicks and the event handlers begin to run, which is called the input delay. This is what first input delay measures, but only for the first interaction. INP measures more than this. It measures the entire interaction and all qualifying interactions, which you'll see shortly. Now, you'll always incur some input delay, because at the very least, it takes time for the browser to receive the input event from the operating system. But that delay can be increased due to tasks on the main thread as the input occurs. Long tasks in particular. If you have a lot of long tasks that are constantly running on the main thread, or even many small tasks, input delays can increase. Once the input delay is over, the event handlers responsible for driving the interaction can run. Now here we see a set of event handlers for a mouse click. The goal here is to ensure that those handlers run as fast as possible. You don't want those event handlers to run for too long, because the browser has work to do after that in order to present the visual feedback the user needs in order to see that something has happened. Once the event handlers finish running, the browser then needs to do rendering, painting, and compositing work in order to present the next frame. This is called the presentation delay, and all this work to present a new frame to the user needs to occur as quickly as possible as well. The presentation delay represents just the main thread portion of the rendering work. There are a lot of nooks and crannies in how long this takes. Some of it is under your control, some of it may be. And it gets more complicated. A single interaction can contain multiple input delays, event handlers, and presentation delays. For example, here you see a mouse interaction where a frame is presented after the user pushes down on a mouse button. But then when the button is released, a new batch of event handlers and rendering tasks must run in order to present additional feedback as the interaction is finished. In cases where there are multiple event handlers in a single logical user interaction, the longest event duration of the interaction will be chosen as the latency for the logical interaction. Now we're ready to talk about how to optimize for INP. When you optimize INP, you're going to want to first measure it, and not just in lab tools, but using field data. Field data is important because it lets you know how your website is actually being experienced by actual users in the field. And one way to gather that field data yourself is to use the Web Vitals library, which there's a link in the lower right-hand corner to the GitHub thing. And I'm also posting slides on my Twitter later, so if you miss this, don't worry. The library exposes methods for each of the core Web Vitals, but also INP. And each method takes a function that exposes properties for the observed metric. Most importantly, the metric name itself, INP in this case, its value, as well as the element responsible for it, provided as a selector string by a function in the linked gist. Now, when you got this field data, and you know which elements are responsible for high interaction latency, then it is time to go to the lab and start testing these interactions, because it is lab tools that will give you a bit more insight into why interactions may be slow. Now, one useful lab tool in Chrome DevTools, starting in Chrome 106, we can now rely on the performance profiler to show interaction details right in a performance trace. So say you know what interaction or what element is causing trouble. You can test that in the performance panel and dive right into that interaction in the call stacks. For example, you can see in the interactions area near the top of the performance trace panel, there's an item labeled interaction type click. This means that this interaction counts towards INP, and we can see that we have a long task in our hand, particularly on the click event, it appears, and we can see that that click event is really running for a long time. This method lets you dive right into what's causing the delay during processing and gives you some ideas for how to break up or optimize that work just a little bit better. Because this particular long task causes quite a bit of delay in the next frame being presented and also can affect your INP. But if you want something a bit more focused, because the Chrome Performance Profiler is kind of a beast on its own, it's a lot to take in, you can see interactions in the new Performance Profiler in the Performance Insights panel in Chrome DevTools. It's a streamlined version of the Performance Profiler we're all familiar with, but a bit easier to use. So you've profiled an interaction, and now you want to know what you can do to optimize it. So what's next? The answer to this is rather complicated, and it depends on your website. And after all, every slow interaction has its own fix, but I'm hoping the following provides you with a general framework or strategy for getting your tasks under control. So one good piece of advice developers tend to follow is to split up work into separate functions. And we do this for a number of reasons, such as maintainability, readability, and testing. It's easier to follow, it's easier to test, and we get to isolate work into separate little discrete functioning units. However, where JavaScript is concerned, because all the work item functions from the previous code snippet are executing in the same function, the do work function, it will group all of that work into a single long-running task. And that's not great from a performance standpoint, because instead of 5 little functions just doing all their own thing and all their own little tasks, you have a big old task that will block the main thread from doing new work, including work that occurs because of user interactions. This will affect your INP if users are trying to interact with your website. You need to break this up. And one way to do that is to yield to the main thread, which breaks up tasks. Now, this is sort of a userland homemade yielding function. It uses a promise that resolves with a call to set timeout. And this works because set timeout will schedule its callback in a new task. Now, with that yield function, you can then yield to the main thread after every little discrete piece of work by awaiting the custom yield function. Note, you don't have to yield after every function. For example, if you have critical work that updates the UI, you can yield after those functions to give the renderer a chance to do that work. The result instead is that you don't have one giant task that has to run 5 functions, but a task for each separate function. And this gives the main thread more opportunities to yield to other things like interactions or background work that the user doesn't necessarily see or care about. Is this approach a bit hacky? Maybe. But there could be a better solution in the future. One proposed part of something called the scheduler API is scheduler.yield, which will work much the same way as the promise-based solution I've shown you, but will allow developers to tell the browser directly if the current task should be broken up and yield to the main thread at specific points instead of relying on hacks. And I'm excited for this potential addition to the web platform, as it will give developers a way to break up work without userland hacks. But I should take this time to remind you of one very important thing. Breaking up work still isn't enough on its own. INP is all about time. Time it takes to present the next frame. If you have a ton of little tasks that are running all the time, or lots of huge tasks that are blocking the main thread, you can't present the next frame after a user interacts with a page as fast as you might need it to. You still need to do as little work as possible. Another way of prioritizing user-facing work is to explicitly yield to user interactions with the isInputPending method. IsInputPending is available in navigator.scheduling.isInputPending, and it returns a Boolean if the user has interacted with an element on the page at the time that it is called. In this code, you can see how the doWork function adds separate functions to an array of tasks, and then within a while loop, this code checks to see if there is a pending user input. If so, we explicitly yield to the main thread so that interaction can take place. Otherwise, we shift the next task off the front of the tasks array, and then we run it. The effect of input pending is evident. Here we have a large blocking task that do work kicks off. However, in the middle of that task, input pending is used to see if a pending user interaction is waiting for the main thread, which in this case is brought on by clicking a button to open a navigation menu. When input pending turns true, we yield to that interaction and allow the browser and the main thread to handle it. But there is more that you can do, and that involves prioritizing tasks. When using this strategy, you should think of tasks in terms of what's critical and user-facing, and what isn't visible or immediate. This figure shows how browser prioritization works by default. When you leave things up to the browser, it will try to prioritize inputs based on a system of internal priorities. It works pretty well, but sometimes it needs a little nudge. The post-task API, currently only supported in Chromium browsers and Firefox behind a flag, adds more flexibility to how browsers can schedule work. Most importantly, it allows the developer to schedule work based on a system of 3 priorities. The first is user blocking, which is for critical work that must run at high priority. Think of this priority as best for interactions that need to be processed as soon as possible. There is user visible, which is for medium priority work that may result in visual changes to the user interface, but maybe isn't strictly critical. And then there is background, which is for low priority work. Think things like analytics collections and beaconing and things that the user doesn't really see or care about. So let's say you have a bunch of work that doesn't result in any changes to the user interface. This would be background work. The shape of the post-task API allows you to create task controller instances, which take a priority value using one of the priorities I mentioned in the previous slide. Then, using the task controller's signal property, we can schedule work using scheduler.postTask according to the task controller's priority. Now, let's say you run that work, and then the user interacts with the page to open a navigation menu, for example. The background work will run at lower priority, but if the user opens the navigation menu, those background tasks will yield to that interaction. This is an exciting API, but even more exciting is that it's still developing. There are discussions currently taking place about adding finer-grained priorities, as well as other mechanisms, such as the scheduler.yield functionality I mentioned earlier. On a final note, I feel it's important to make it clear that INP is a developing metric. The Chrome Speed Metrics team at Google is still fine-tuning this metric, so some of what I said in this talk may change, but the fundamentals should still hold true in the future. If you have any questions about INP, feel free to ask me in the hallway or at the after party. I don't know everything, but I'll try to answer to the best of my ability. I try my best, but you may stump me, but I'll try. I will also tweet the link to my slides soon, which you will see shortly on my Twitter profile at Malchata. That's M-A-L-C-H-A-T-A. And with that, thank you for your time and hosting me in your incredible and amazing city. It's been both an honor and an experience I'll always remember. Thank you.